Okay, let's start. First, I think we get some feedback from last lecture, right? So, uh, because we have too many groups in this lecture, and we also uh, have a lot of material we want to cover. So, also from the feedback, it seems that it's okay from your side that we don't continue the presentation in the class, right? We will do it offline. But because this was only last minute kind of decision from our lecture on Tuesday, so for today's presentation, actually we may have 5 groups, but we give the option that if you really want to do the presentation in the class, you can do it. Or all the remaining groups, uh, we will create oh, actually, we don't need. We already have the assignment for you to submit your presentation slides. But in this case, if you haven't presented yet, and please also submit the Zoom recording of your presentation, and I will watch through them and give you feedback on the score. Okay, so let me first check for the groups who was originally scheduled to present today. Any group who really want to do the presentation in the class? If so, you can put it in the chat box. I will wait for 20 seconds. If I don't, after that, I will apply accordingly all the time.
Russ, I have a quick question.
Mhm.
If we do present in class, sorry, if we don't want to present in class, do we have like to the end of the day to present or to submit a presentation?
Sorry, say that again?
So if we don't present in class, for the
Mhm.
people who are presenting today, do we have like a deadline to submit our presentation?
Uh, I will make it a little bit later, so you have enough time to prepare.
Got it. All right. Thanks.
Okay, so basically with group 15 still want to do that, and group 24, right? Okay, so we will have 2 groups do the presentation, and let me count. That will take roughly half an hour, and then I have remaining maybe 45 minutes to do the lecture part, which is good. Okay. Okay, let me continue with my lecture, and we will again that will be covered in your quiz. Uh, last time we talked about the uh, uh, domain resource fairness. Uh, let me see. Uh, yeah, this probably okay. Let me give you a high level idea, right? But don't worry for this paper. We won't have asked you any question in the quiz, but you can get a high level message. So this one handle the problem that in the data centers, the communication, right? So if we have a lot of senders in the communication in the data center, send through the switch, right? Then you may get congested in the switch, right? That is the problem. And uh, so there is something called rate-based congestion control, right? But the issue is there is that as you have more senders, right? The sender they need to build up the queue, right? That at the switch in order to uh, do the rate control, right? But the problem is that if you have n senders, right, and each sender may have multiple flows, right? So then as the number of flows increase, the queue length also increase, right? But the queue length increase, that causes an issue, that is your delay. Your latency also increase, right? That is a problem with the traditional solution. Right? This is what they show in the practice, right? As the x-axis is the number of flows. As you can see, as the number of flows increase, right? So the data queue, the queue length also increase a lot. But this credit-based, right, is a credit-based approach is what they propose here, right? So instead of using the queue, so they can give the credit to the flow and to use to spend, right? You can see in this case, the queue length is much smaller. Right? That is a key message from here. This is basically architecture, but it's a little bit complicated, so we'll skip it. Okay. Okay, so this one, this is another paper regarding the code flow scheduling. That is following also on the networking side, right? So because if you are familiar with the networking, right? So traditional, when we schedule the resources, we schedule based on individual flows. But in this case, they consider a different one called code flow. That is a main novelty here, right? So of course, right, if you can decrease the code flow's complete time, you can save uh, the time for job, right? But minimizing the average code flow complete time is a bit hard, right? This is different from the traditional flow. The code flow means that, for example, in MapReduce, right, the shuffle phase finish only when the last one finish. Therefore, if you consider the shuffle, each individual communication between two servers, those are one flow, right? But shuffle is basically all to all, right? So you get a lot of flows together. But we call them this set of flows a co-flow because in this case, we need to wait until the last flow to finish. Right? As you can see, right? So the co-flow is clearly much harder, right? Because if it's only individual flow, the easiest algorithm to minimize the completion time, average completion time, is that we serve the smallest flow or the shortest flow first. Right? So that can minimize the waiting time, therefore minimizing the average completion time. But for the code flow, it's not always that case because the code flow has many flows there, right? So when you say if high level idea, you still want to prioritize a smaller code flow. But what do we mean by smaller, right? If you want to aggregate them together, or the longest flow in the code flow, or what should be, right? So this is what the paper suggests, right? So they will use this smallest code flow first, right? And this is when you have the complete information. And when you don't have the complete knowledge, for example, before the flow start, you actually don't know the size of the code flow. Right? So this one, the traditional way is that we just say which one gets the least service so far, and then we serve that one. This is a mimic of the smallest flow first, when we have a complete knowledge. But now, if you have n flows, if you don't know which flow is the shortest, then you cannot do the smallest flow first, but you can do the kind of serve the flows equally, right? Then the smaller flow will also finish the first, right? So this paper is trying to do this one on the code flow scheduling, right? And yeah, there's too much details here. Okay, but I think given the time we consideration, that's basically the message you need to know about the code flow scheduling. The details we ignore them. But if you're interested, you can definitely read those papers. You can see the details. Okay, the I can continue with the second part. It's large scale computing. Let me. Okay, so we talk a little bit about, right? So the current trend from the last two decades is basically we go from personal computer to either high performance computing or cloud computing. Right. So these two are also traditional very different. Even though with the AI machine learning tasks, they start to have more overlap, but still very different. Okay, so I say what are the differences? Right. So HPC, high performance computing, right? They target extremely large data set and process the information in parallel. Where I highlight here is that while sharing the data between computer nodes. Right? In contrast, cloud computing, right? They also, of course, try to handle large set of data, right? And process the information in parallel. But the difference is that there is a little or no effort to separate the problem into a number of parallel tasks. And also there is a limited data sharing among the tasks, among the computer nodes. Right. And basically for cloud computing, the problem they handled is the so-called embarrassing parallel problems, right? Like what we discussed in previous lecture, like word count, right? If you want to count the number, the occurrence of different words in a large amount of documents, right? Then you can just divide the document in the chunks, right? And then you ask each compute node to do the word count for a given set of documents. And then there is a little effort needed to separate the problem into potentially large number of parallel tasks, right? And also, when each computer node work on its own documents, right? So basically, they don't need to communicate with other nodes, right? Except that once they finish their word counting, right, we need to do the shuffle to collect all the information and then to get the final result. Right? But on the other hand, the HPC, the problem can be very complicated. For example, to simulate the climate change. Right. So it's not something you can just do the climate change for each individual disease, each individual location, and then sum it up, right? No, because they have a very complicated nonlinear impact on each other. Right? So this is a traditional difference. So basically what I just mentioned is that HPC, because the problem is not easily can be decomposed into smaller problems. And they need a lot of communication and coordination among the computer nodes. So this one is often called vertical scalability, meaning that by adding more nodes and do the high performance computing, we actually increase the capability of the problem solving. Right? We can solve actually more complicated problems. On the other side, cloud computing is just it's a similar problem. It's just that we can do in larger scale. If we only have one node, we can only do, for example, process 1,000 documents per second. But if we have a 1,000 node, we can process at 1 million documents per second. Right? This is called horizontal scalability. Right? So this is a figure I found. Right? So the left part is the cloud computing. Sorry. The left part is a high HPC. So as we mentioned, the data is stored in one location. and then the computing is another, right? So the compute node also coordinate, they do a lot of communication through the fast interconnect, right? Which is you can consider the ancestor of current MV link or MV switch, right? And all the node process shared data, right, together. The right hand side, the right one, this is cloud computing, right? You can say we first divide the data into smaller chunks. And then we, each compute node just read one chunk of the data. And normally the data is local to the compute node. And they are only connected through the traditional Ethernet, which is very slow. But if you don't need a lot of coordination, we can do that. Right? So you can see also from here that the left-hand side, high-performance computing, have higher requirement on the hardware and also the system software, while the left-hand side is much easier. So there is a very good description of the difference, right? It's like if you have a 200 school kids, right? If you want them to each pick up a piece of paper on the floor, that is what we call the EPP, the embarrassing parallel problem, right? That scales really well and really easily in the for cloud computing. But if you want to coordinate them to play a show, a ballet show, for example, then that problem is more like a high performance computing, right? It doesn't scale easily, and you need a lot of coordination among them, right? And here you probably need a lot of teacher, a lot of instructor in order to do that, right? The requirement is also much higher, both on the instructor side and on the on the student side versus the first task. Okay, so now we have infrastructure. I mean, for both HPC and cloud computing, right? So we already mentioned cloud computing, three main provider: Amazon, Microsoft, and Google. Right? HPC, actually, there are a lot of HPC or supercomputer center built in the United States. The Department of Energy, they build a lot of supercomputing centers, right? And other for example, for energy, for climate, right? So there are also other high performance computing or supercomputing centers built. So when you want to use HPC, right? When to use HPC, basically you need application that you really want to push for performance, right? So for example, for computing, right? So normally we have the accelerators, right? Even in the old days, right? When the GPU is not widely used, but there they do have a lot of accelerators. And they also do parallelization in the processor unit. And the library, the software hardware library, is also optimized for that particular application. They have the fast interconnect, both for the hardware, that is infinite band, also for the software. The software, they will develop a message passing interface or MPI, particular for the communication among the processors. Right. The storage, they also need a high performance storage so that to optimize read and write rate. Okay, so also for this one, the computing, the communication, and the storage, those ones are often, they could be optimized based on the application. And here, each application can be very large one. For example, the climate change or the nuclear plant simulation, right? A lot of, they are very mission critical. Each application itself is a very big one, right? So, right. On the other side, when to use cloud computing, right? It's basically when you have a problem that can be easily parallelized, right? Then you can use this one, right? Then it doesn't rely on the fast shared memory or storage. You can easily split the data into several pieces for parallel processing. And this is another one, right? If you don't want to uh, use the resource all the time, right? You only want to pay as you use, right? This is the opportunity that sometimes even for some HPC problems, they are also use cloud computing, right? That is because if they do it in a separate HPC center, right, then if the utilization is low, then they pay a lot of high cost, right? But if you go to cloud computing, they can just pay as you go. We will come back to this one later, right? That is where I say they are start to have more overlap between HPC and cloud computing. Right. This one is following the third bullet point, right? So you want to get a lot of resource for just for a short time period. Right? You don't want to do the big capital investment at the beginning. Also, if you want to use virtual machine, right, instead of uh, right, so the so you can choose the operating system and the applications. Cloud computing is also a good choice for you. Okay. So, okay, other than the HPC and the cloud computing, there is also a comparison between local computing and cloud computing. Right. So we also know the difference between these two. Right. Also the pros and cons. So you can know when to use which. Right. So basically, right. So when you do the local computing, you have access to the computer. Right. That is fast and easy. Right. So, for example, many students here are from data science or computer science, right? In the future, right, when you need to process a lot of data, right, you also need to decide where to put your data, right? You can do the computation locally, or you can go to the cloud. Maybe in the future, you need to propose the solution to your manager, or if you are the manager, you need to make the decision, right? So here are the some considerations uh, you can take, right? So take into, right? So like if we have a computer room, for example, in the local building, right? Then first, because it's not far away, you may have a very high speed connection to that computer, right? Versus for the cloud, right? So the cloud, you need to go through many, many steps in order to get the connection, right? The delay could be larger. Also, even the physical access to the computer is easy, right? If you want to go there to check something, you can just get into the room. You get access to everything, right? But in the cloud computing, right? If you want to check the hardware or something, you cannot, right? You even don't know where they put your task on in many cases. Also, you may feel more comfortable, right? Because you have the full control of the data, right? So it removes the safety and data ownership concerns, especially if the data is very sensitive, right? If you put it on cloud computing, right? So the cloud provider, they actually no one has a perfect solution for the safety or the privacy of the data. Right? So we heard a lot of news about the data leakage, right? But there is also another uh, opinion, right? So it depends on how well you can do the local computing, right? If you have a very specialized team, you have the expert to help you to build the security measures, right? So then local computing might be safer compared to the remote one, right? But if you just have a regular local computing room without those particular security expert or security mechanisms, then your local computing could be very easily attacked compared to actually you go to cloud computing, right? Because there they have more experts, they can actually protect the data to a actually a fairly good level. Okay, but on the other side, to do the local computing costs, right? You need to invest in facility and maintenance. But if you already have the local facility, right, then you may avoid this cost. Right? This is what happened, right? If in some organizations they already have the local computing center, then you probably can make use of it. Right? Also, right, but you may have a lot of local team access to the facility, right? So you may not get enough resources, right? Uh, like for example, local for AI Institute, we have some very powerful AI servers, right? But it may not be always available. If it's occupied by other researcher, you will have to wait. And of course, if you have some uncertainty, you don't have the flexibility or elasticity, right? Like what we can get from cloud computing. Okay, what we show here, the downside is actually the pro of the cloud computing, right? The cost, you can just pay as you go. But remember, previously discussed, even you can do pay as you go, but you may have a, a high cost compared to if you use it locally, but you use it all the time. So the utilization is also another consideration. You can get a large computing capacity quickly, right? And only for time you need it. And that can serve the elasticity, right? That is also important. So nowadays, we already moved from the traditional the virtual machine style to the current serverless computing, right? Or basically use containers. And even in cloud computing, they start to have this function as a service. Basically, if it's a lot of access is based on particular function, right, then you can do this one. Right? So it might be relevant for uh, the current AI machine learning, right? Because especially for both of them, right? So what you use, either training or inference, it's very standard, right? So this gives the opportunity that they can focus to serve the particular function instead of giving you the just some servers and then you manage it by yourself. Because you need the internet access. And also, right, once you go to the internet, you have the security issue, right? And you need to configure the network correctly. Otherwise, you may lose all the access. Ownership and access control, right? So extreme case, right, for privacy, right? So a lot of data like your house, if your for your personal financial information or other information, you don't want to share with others. Then the best way is that you never generate the information or you never let the information go out of your local control. Right? Because once it go into a third party, then you basically have no control over there. Right? That is also the current trend for edge computing as we discussed, right? Or there's another one called federated learning. Try to still do something jointly, but keep the data local. There are also hardware that trying to incorporate the security issue inside the hardware, right, to further increase the safety. Another is, as I mentioned, right, if you use a service all the time, cloud computing, actually the cost would be much higher, right, compared to you just buy the server and manage it by yourself, right? Because that is where the cloud provider make money. Okay, so the particular one as we discussed, for HPC, start to uh, do that in the cloud, right? So the proportion of all HPC sites worldwide, they start to run some workload in the public cloud, right? They increase a lot for the reason we discussed, right? Because the HPC workload is not consistent all the time, right? Sometimes it's high, sometimes it's low, right? For those peak periods, it may not make sense to maintain the facility for all of them, right? But probably you can move that to cloud computing, right? So also in HPC, not all the HPC workload are very complicated one, right? Some of them can actually be served in cloud computing, right? That is what we say. Right? So this one continue to increase, and this created the opportunity. Right? Actually, when I prepared the slides, that was before the current trend of transformer, right? And also the NVIDIA, they start to build the GPU server that is already similar to those used in HPC, right? And those servers are start to be deployed in cloud computing, right? This further add to the trend that we will see more HPC in the cloud computing, right? Because HPC workload are often more valuable, right? That's why at the beginning people can invest a lot of money to do those supercomputing centers. Right? So they can build one supercomputing center just for a smaller number of applications. Right? That is also different from cloud computing. Right? So in those HPC, they will write a particular software and the library and build the dedicated hardware to do that. Right? To some extent, this is similar to like cryptocurrency mining, right? Because the value is so high that they build specialized hardware and to combine with some software to do that. Right? And also similar to the current large language model training. Right? In this case, we start to see the trend compared to traditional MapReduce, which is very simple, very easily parallelizable. The current training, because the model is very large, we need to divide the model into small pieces and put them each on a different GPU. And therefore, each GPU node, they only hold a fraction of the whole model. So they need to communicate with each other. Right? So from that perspective, you also see they start to have more property, more characteristics in HPC. And that's why the hardware that we start to have the high-speed interconnect. Right? And the storage, the memory size is also large. Right? The GPU is a specialized accelerator. Right? So actually, if we go back to the previous slides, right? So, sorry. You can see here, right? So the current large language model training, right? They start to use the specialized hardware accelerator, right? So the GPU you can consider is you can think about single instruction as a really huge amount of data processor, right? And the library, right, like the CUDA, right, is a library they develop a particular for this machine learning task. They already use the NVLink there, right? Of course, they don't use MPI, but I think communication in the future, they may develop something particular, right? Storage also. Right? So that's why we start to see on the one side, a lot of HPC, they run part of their workload in the public cloud. Either it's because it's at the peak, or this workload, even though it's part of HPC, but this one are suitable for cloud computing. Right? Meanwhile, the cloud computing now, because we start to serve those large algorithm training, right? Workload like those. It's also start to become more like a traditional HPC. Right? This is something like if you really use the communication MPI, right? Let's go to HPC, right? But of course, sometimes you have the high latency, right? Right. So that is may be used for cloud HPC, and for cloud computing, it's mainly for the embarrassingly parallel problem, right? Like the word computing. Okay, let me see. Yeah, I think I still have maybe 10 minutes. Yeah. Okay, now we talk about the large scale computing using Google File System and MapReduce. Right. So the problem, as we already talked a little bit about both, right? But at a high level, the GPL, Google File System, the GFS, they try to store large amount of data, right? Efficiently, fault tolerant, and scalable. Right? And MapReduce, they want to process a lot of data similarly, right? Efficiently, fault tolerant, and scalable. Right? So the requirement is similar, and these two they have a lot of things in common. Right? They have the common assumptions. Failures are not. The high concurrency is the most important part. And they do the batch processing, basically focus on throughput over latency. Right? This is more like uh, the large language model training instead of the inference. And they also do the code design, right, to increase flexibility. So if you just do a general solution, right, you cannot make this kind of a particular design, right? That's why for Google File System and MapReduce, they were developed for the application in Google particularly. Right? They are not aimed to become a general solution. So there is a synergy between storage and computing, right? Symbiosis. So how we store the data often dictate how we can operate on them, right? For example, MapReduce normally you need to go to the computing go to the storage, right? So how you store the data definitely have a high impact on the processing. And also how you plan to process the data also dictate how we store it, right? Whether you read a lot or write a lot, right? Clearly have a high impact on how the data should be stored. That's why normally for a particular application, storage and compute need to be jointly designed. And this is not a one solution fit all, right? It's application driven. Eventually, right, it go to the workload. What type of data and what do you want to do with the data, right? Even for now, for AI machine learning training inference, those are still the same. Right? It's just a workload change. So now what is a workload? Right? For Google workload, it's they don't have a lot of huge files, right? Because most of the file are just web page, right? The web page won't be very large, right? And the files are write once, mostly appended to, right? For the web page, basically when you do the crawling and you store it locally, right? Write once. Later, if they are update, normally you just append some data there. Some are never read again, right? Because a lot of web pages they are useless. Right? They have no user, no visitor at all. Right? So those are considered as code data. But the read for each of the Google search we do, right? It need to go through a huge amount of data reads, right? And this is also streaming, right? Need to read in real time. right? So that we should optimize for the rate. The latency, right? So a lot of the processing, right, except for the final result, right, are pre-calculated, which we will discuss in the next component of the course, how Google do the page rank and the Google search. Right? So they are not user-facing, so they don't need to worry about the latency a lot. Right? On the other side, nowadays ChatGPT, right, is user-facing, right, and it's not the when you ask the question, they start to generate, process your prompt, and generate the result. Right. So they cannot do a lot of pre-processing. Right. That's why compared with Google search, using the ChatGPT, especially the question is long, and you need to wait a significant amount of time until you get the full answer. Right? So this is also different. Okay, so here the file system is very important, right? So it's sit between the hardware and application, right? So the hardware can change, right? You can use a hard drive or change it to a different type of hard drive or even SSD, right? They can continue to use Google File System. Application, right? So a large number of applications at Google, they use this Google File System. And this is similar to the IP protocol in computer networking stack, if you are familiar with that. Okay, so the Google file system, the design decisions, therefore, right? First file stored as chunks, right? They are fixed size, and the size is not very large, so that most of the files, the web pages, can be stored in one chunk. And of course, the issue here is that the web page may not be large enough to use all the chunk, right? So, but it's okay because the data only stored in the storage, right? So it's not a memory. So wasting some of the space is okay to trade off for the easier management. And for similar reason, right? They use replication for reliability. They just simply duplicate each chunk, right? Because the disk is fairly cheap, right? And this greatly simplifies the whole design. And they have a single master node, right? Similarly to simplify the design. And they didn't do any data caching, right? Because you have a huge amount of data set, right? And the streaming rate. If you have a data caching, you put some material there, but the next read, the hit rate of the caching may be very low, right? Compared to like social network platforms like Facebook, right? So they do the data caching a lot. Right? It's a very different application workload, so the design choice is also different. They use familiar interface, but customize the API. So, for example, do the snapshot or record append. This is the architecture, right? Okay, let's talk about this one more carefully. So, as you can see, this is the master node. The master node basically keep the file namespace. And from here, for the leaf node, it's a particular file. And it will contain the location, the chunk name, chunk ID, and the location of the chunks within that file. Okay, that's basically the master node does. Maintain the namespace and also the location, the mapping from the file name to the chunk index, and of course the location. Then, if you are a client, right, you will send the file name and the chunk index, basically which chunk among the file you want to get access to, right? And then the master node will check the file name and then give you, based on the index, give you the chunk handle and the chunk location. The location basically is the chunk server location. That's the only communication between application, the client, and the master node. Right? Because we only have a single master node, so this communication need to be simplified as much as possible, right? Because you can imagine there is a huge amount of the client want to talk to the master node, right? Also, if the message they send involved in this communication is also very simple. It just control message. Each message is very short. Okay, one question, are the slides posted to Spreadspace? Not yet. I will do that after this class. Okay. So the real work is done between the client with the chunk server. The chunk server, they will run a local Linux file system, right? So basically, the client will send the chunk handler and the byte range. By default, you may get all the bytes in the chunk. And then the chunk server will send back the raw data, the chunk data. Right? This, as you can imagine, could be very bandwidth consuming. But it's okay because we have a huge amount of chunk servers, right? So each chunk server may send the data back, right, to also potentially large amount of clients. And between the master node and the chunk server, right? So the master node can give the instruction to the chunk server, and the chunk server will update with state, right? For example, right, whether you are still alive or goes there some issue, right? The chunk server may send the master node will ask the chunk server to do some have some new data, remove some data, or do some recover of some data. Okay, so I think I will stop here. Then let me also put a note here. Uh, this is an material for mixture. Okay, now we have two groups to the presentation. The first one is group 15. Are you ready?
Can you give us access to share?
Yes, you have it.
All right, sorry, let me just open slides here.
Yeah, for these two groups, please everyone, please also do the feedback. By the way, I want to emphasize the feedback form is used for your participation, active participation in the course, right? And for that reason, we have your name and ID there, right? So be more responsible in writing those. And you can say, we can also say that, right? If you write something that no sense or you give a very low score, right? So we have the record, right? So keep that in your mind when you do that. Try to give something useful and constructive. Yeah, please.
All right. Oh, hello everyone, we're group 15. Our project proposal is about comparing ChatGPT 4.0 and the new model OpenAI's o1 for high-level problem solving. And today is just a kind of like a stepping stone in terms of really getting to understand GPT 4.0 and the introduction to OpenAI o1. Right, so first I just wanted to give a quick timeline of how OpenAI's models evolved. So starting first with GPT-1 in 2018, it was the first model. It made the baseline of introducing unsupervised pre-training and natural language processing tasks. It pretty much made the groundwork. GPT 2022, it made a great leap in terms of the model size and capabilities. However, it was withheld for potential misuse. In 2020, we got GPT-3, which is the breakthrough really, and it's 175 billion parameters, introduced few-shot learning, and a model perform tasks with minimal examples, broadening and application within NLP. In 2022, we got GPT 3.5, um, GPT 3.5, which enhancing its performance and efficiency. And then now GPT-4, the multimodal capabilities were introduced. And this year, we got two models, 4.0 and 0.1. While those models they are the most updated, they're the best of the models. 4.0 is focused on multimodal work nowadays, and zero 0.1 is more on the thinking before responding, right? And I just want to give a very quick overview of the difference between NLP task or a rule-based task and an adaptive learning task. So for NLP, we have the rule-based. It is designed for a very specific narrow task, and it's usually trained using supervised learning, while NLP is used unsupervised learning and then supervised for the fine-tuning aspect. Therefore, the LLM is used more and has a lot more flexibility in terms of power. Then here is the transformer architecture, which uses the attention mechanism. Just want to go quickly into this because most of us know this. So we have the first section, which is the encoder. The input goes through several layers. The multi-head attention, it computes the attention of different aspects of the input in parallel, allowing the model to focus on multiple sections of the input and parts of the sequencing simultaneously. Then there is the feed forward, which is pretty much a simple neural network that processes the tokens after attention, improving their representation. And then there is normalization, addition to the residual connections. And then we have got the decoder, which pretty much like the encoder has very similar structure, but it has a masked multi-head attention that prevents the model from really looking forward when it's doing the prediction during the training section. And then after all that, everything's passed to a linear softmax to reduce the probabilities for the next token. And then quickly recap, here's a question. Which one of the following is the mechanism for models like GPT-4o? All right, let me open the chat here. All right, it is an attention mechanism. Right, I'll pass it on.
Great, thank you. So now we'll be talking about the limitations of ChatGPT 4o, and I'll list a few, specifically limited context retention. So that means that ChatGPT won't remember as much from the beginning of the conversation as where you are now. In addition, it is very sensitive to input phrasing. So minor changes or removal of words in your input can drastically have different responses. For example, what are the benefits of exercise versus why is exercise important? They have the same meaning, but the outputs might be different. So following that, there is inconsistent output. Even if you put the same input, you might have different outputs because the process within ChatGPT 4o is stochastic, right? It uses probability distribution, so outputs will vary. In addition, ChatGPT 4o can hallucinate information, which means it creates factually incorrect or non-existent information out of nowhere. It also lacks its explainability and transparency, so it does not explain its thought or mythology that 0.1 will explain. Next slide, please. So here's a question for everyone. Can y'all name some alternatives to ChatGPT's 4o? Claude, great. Yeah, next slide. Exactly, right? Claude is a great example. Gemini is also a great example. And Watson X. So all of these have their own pros and cons, and it depends on your use case scenario. So for Claude, its main focus is on safety and ethical AI, right? So that means it prioritizes ethical interaction, and there's also a transparency in its response. It explains reasoning step by step, and it's also simpler compared to ChatGPT 4o because it has a smaller training size, and it costs less compared to Gemini, Meta's Google's Gemini, right? It has real-time access to the Google search engine and it has multimodal capabilities, which means it could handle both text and images as well. And finally, Watson X, which is able to focus on domain-specific industries like healthcare, legal, finance, and it makes it highly effective in these fields. And it has enterprise-level integration, which means it could work coherently and together with existing IT infrastructure, cloud services, and business workflows. Next slide, please. So how can AI be combined and used together, right? So for example, we combine predictive AI from IBM Watson and generative AI, ChatGPT 4o, highlighting each tool's strengths and making the best outcome possible. So you can use Watson AI to predict market trends, and then 4o to generate responses, personal responses. So an example in the health customer service, right? Watson Assistant can predict customer needs, and then 4o can use this to generate personalized responses in real time. Next slide. So what about how can it use combined with emerging technologies, right? So one way that generative AI and Internet of Things is used is because IoT systems can generate a lot of information. So generative AI can process this information effectively, leading to meaningful insights from the predictive model. So it has increased efficiency, which means it reduces energy consumption, improved workflow, it gives a personalization, so personalized recommendations and whatnot, and real-time decision-making, making it more accurate across industries, and also able to scale across large amounts of data. I'll pass it off to Sopal now.
Thank you, David. Now I'll discuss GPT-4's performance evaluation, the industries using GPT-4, and future uses case for OpenAI o1. In the GPT-4 technical report, GPT-4 showed notable improvements over previous models like GPT 3.5, especially in benchmarks in MMLU and HelloSwag. Could you click once for me? However, it performed relatively lower on tasks like human eval, which includes Python coding with 67% accuracy, and drop, which includes reasoning tasks with 80.9%. These results highlight some limitations in advanced reasoning and coding. Now, with the release of OpenAI o1, we will explore whether this model can improve on GPT-4's shortcomings, particularly in these areas. Next slide, please. OpenAI introduced OpenAI Evals, an open source framework for creating and running benchmarks. This allows us to evaluate models like GPT-4 and OpenAI o1 directly, comparing their performance on the same task. By using OpenAI Evals, we can track how well OpenAI o1 addresses the limitations seen in GPT-4, especially in advanced reasoning and coding tasks. Next slide, please. GPT technology is already widely used across industries. In tech, companies like Microsoft integrate GPT-4 into Azure AI for chatbots. Finance firms such as Morgan Stanley use it for summarizing market research, while in healthcare, Mayo Clinic employs it for diagnostic support using patient data. In education, platforms like Coursera leverage GPT for personalized learning, and in software development, tools like GitHub Copilot assist with coding tasks such as debugging. These examples show how GPT is transforming various sectors. Next slide, please. OpenAI o1 presents exciting opportunities for the future. With its ability to handle complex tasks and solve more difficult problems in science, coding, and mathematics compared to previous models, it has the potential to transform various industries. In robotics, it could drive AI-based decision-making and automation. In software development, it may automate more advanced tasks, leading to faster and more efficient development cycles. In finance, OpenAI o1 could enhance real-time decision-making, improving risk assessments and trading strategies. Autonomous vehicles might benefit from the more accurate navigation and decision-making processes. Overall, OpenAI O1's ability to tackle challenging problems positions it to expand AI's role in these industries and beyond. Next slide, please. So just for a quick recap, which two benchmarks did GPT-4 score relate to lower on? And the answer is the next slide, please. C. It includes Python coding checks and reading comprehension. Thank you. These are references we had.
Thank you. Any questions? Yeah, thank you for talking with this one. So I don't need to go over that by myself. So now, yeah, indeed, I like the presentation of your group in both classes. Yeah, one quick question, right? So, can you talk more about how this can help other students or other projects?
Yeah, I can talk a little bit about that. So now with OpenAI's O1 model, so the focus of our project is really comparing which one of those is more suitable for high level problem solving. Because getting into the industry and as everything goes into more of the high level questions, because now ChatGPT is going to be taking over the lower level kind of like Python hello world kind of questions, and we need more high level answering. So so what the purpose of this project really is to understand, should we be using the generalized GPT-4o for our high level questions, or should we utilize the chain of thought kind of like think before respond OpenAI model? I know OpenAI model right now it's only in preview, so it doesn't have the full capabilities of like searching the internet and so on. However, we kind of want to understand when asking questions that are high level coding or high level mathematical questions, do we rely mostly on the thinking aspect or searching the internet and then finding the answer? And this is kind of like it would help a lot for students who are going into interviews, coding interviews, or people who need help with if they were stuck on a homework question or they were stuck on a debugging question. Yep.
Yeah, I think the interview will also be changed significantly in the coming years.
Yeah, 100%.
During the pandemic, the IT company just use a question from the leak code or leak code substance standard, right? But now, if you do that, especially in a remote manner, they can have the ChatGPT directly answered. Okay, good. As everyone, please submit your feedback. Another question in the chat box. Metrics.
Oh, metrics. Let's
So
go
that
back to
part, I can explain it. So you can see the benchmarks that OpenAI gives the technical report of the GPT-4. We refer these benchmarks. They had an open source evaluation that we can use the same evaluation metrics to compare the GPT-4 and OpenAI O1. So basically, we have an open source named OpenAI evals to evaluate it.
Okay, sounds good. Let's move on to the next group. Next one is group 24. Yeah, I mean, in the future, if I see some group, the recording is really good, and I may invite them to do the presentation in the class, but that will be the limited case. Right, so, yeah, feel free to start.
Hello, everyone. So we're group 24, and today we'll be presenting on gender bias in co-reference resolution.
We cannot hear you.
Oh, I'm so sorry. I'm so sorry.
Oh.
Oh, yeah. So, hi everyone. We're group 24, and today we're presenting on gender bias in co-reference resolution. So I'd like to begin with a question. So does anybody have any idea what co-reference resolution is? I'll give you like about 10 seconds to think about it and maybe come up with something. Okay. So in the interest of time, I'll carry on. So co-reference resolution is actually the task of identifying when different phrases in text refer to the same entity. So this is kind of fundamental for understanding and processing natural language. So I'll give you an example which will make this much clearer. So in this example sentence, we can see that it contains pronouns such as he, me, his, etc., which sort of like create ambiguity about which entities they refer to. And after co-reference resolution, these pronouns are replaced with specific names or nouns, making it explicit who or what each pronoun refers to. So there's a paper titled Gender Bias in Co-Reference Resolution, Evaluation and Debiasing Methods, which investigates how co-reference systems can exhibit gender bias, often linking gendered pronouns to stereotypical bias or roles. This work has been influential in raising awareness about gender bias in NLP and has spurred further research into developing fairer and more accurate language models. As you can see, it's a really highly cited paper. So, what are the different co-reference resolution methods? So, it has seen an evolution over time, and there are various approaches. The rule-based approach, like the Stanford deterministic co-reference system, uses pre-defined linguistic rules to determine co-references. While interpretable, these struggle with complex tasks. Then there are feature-based approaches which leverage machine learning alongside engineered features, which allows learning from data, but it relies heavily on manual feature design. And more recently, the neural network-based systems which leverage pre-trained embeddings and deep learning, which are being used and can automatically learn relevant features from context. However, these models often lack interpretability. So, what exactly is the problem that we are trying to solve here? So, NLP systems often rely on training data which contains stereotypical biases. This reliance can lead to like biased performance, particularly affecting certain groups which are like underrepresented. This could lead to inaccurately associating gendered pronouns with stereotypical roles, which in turn impacts fairness and accuracy of the results. To test this hypothesis, a new challenge corpus was developed, which is the Winnow bias dataset. So, what does the Winnow bias dataset contain? It is a dataset that contains Winograd schema-style sentences, which represent about 40 occupations based on the US Department of Labor statistics. It mainly contains two types of challenge sentences with their pro-stereotypical and anti-stereotypical form. So type 1, where decisions must be made using world knowledge about the given circumstances. Such examples are challenging because they contain no syntactic cues. And type 2, which can be resolved using syntactic information and understanding of the pronoun. We expect systems to perform better on these type of cases because these contain both semantic and syntactic cues, which help with disambiguation. Now moving on to like Ruhin.
Yep, thank you. So our initial evaluation. Now, all three types of co-reference resolution systems were evaluated based on the performance on the Winnow bias dataset. They were evaluated using co-reference scorer. Now, despite qualitatively different approaches, all systems exhibit gender bias, showing an average difference in performance between pro-stereotypical and anti-stereotype conditions of 21.1 in F1 score. Next page, please. The causes of gender bias in co-reference resolution. Does anyone want to try what causes gender bias in co-reference resolution? So let me go ahead with the slide and I'll answer the question. So in order to study the source of this bias, we actually analyzed the training corpus used by the systems. The training corpus used by the systems were Onto Nodes 5.0, which is a large multilingual annotated dataset used for various NLP tasks, including co-reference resolution, named entity recognition, semantic role labeling, and more. It covers multiple languages and genres and provides rich annotations which help identify links between different mentions of the same entity, making it a standard resource for training and evaluating NLP models, especially for co-reference resolution. Now, but this dataset exhibits a severe gender imbalance with over 80% of entities mentioned with gender pronouns being male, and male mentions are more than twice as likely to include job titles compared to female mentions, a trend that persists across different genres. The bias is also due to resource bias, where word embeddings widely used in NLP applications are severely biased. An example being, men tends to be closer to programmer than women in glow embeddings. The use of gender statistics in feature-rich context can lead to bias by disproportionately emphasizing male noun phrases associated with professional roles, thereby reflecting societal stereotypes and reinforcing gender inequality in language processing. The solution. The first being gender swapping. Now, to eliminate gender bias, the training corpus was created by swapping male entities with female entities and vice versa, while maintaining non-gender revealing correlations. This is done using a rule-based approach where name entities are anonymized and a dictionary of gendered terms is used to ensure consistent gender swaps throughout the corpus. The next being debiased word embeddings. So the debiasing process removes gender components from neutral words while preserving them for gender-specific words, resulting in new word vectors that maintain semantic relationships but reduce gender bias. Replace glow embeddings with debiased vectors. And the last is gender list. To address bias in gender statistics, we balance the counts of male and female noun phrases by ensuring equal representation in the feature list derived from external resources. Over to you, Tony.
Yeah, thank you, Rohit. So now let's take a look at how the systems performed on the winner bias development set. So evaluation of the systems were done on different types of sentences. As you see in the columns, the T1P and T1A represent tasks where the system needed word knowledge to solve for pro-stereotypical and anti-stereotypical sentences. And the T2P and T2A are for tasks where the system could rely on sentence structures instead. And the last column, as you can see, the difference column, it shows how much more biased the system is. The bigger the difference, the more biased it is. So without any debiasing techniques, the difference was quite large, meaning the systems were handling gender stereotypical situations with a lot of bias. Next slide, please. Hello. Hi, Vedha. Can you move to the next slide? Yeah. So now after applying the debiasing techniques, we see a big reduction in bias, especially with the E2E system. By using methods like anonymization, resource augmentation, and data augmentation, the system had the smallest type bias in type 1 tasks with only just a 1.1 point difference. That's actually a huge improvement from before. The feature-based methods also showed less bias, especially when all techniques were applied with just a 0.2 difference in type 1 tasks. However, the rule-based system didn't show improvement because it isn't actually trainable like the others. Moving on to the next slide. So now let's look at the results from the winner bias test set. The debiasing techniques worked really well to reduce gender bias, and the system still performed strongly. A common concern with debiasing is that it might lower the system's accuracy, but that wasn't the case here. These systems performed well on both the winner bias and the on-to-node datasets, showing that the methods were effective and didn't sacrifice performance for fairness. So moving on to the next slide. Next slide, please. So, no, the previous one, sorry. Yeah. Yeah, so here's an interesting result from the gender reverse dataset. So, I have like an interactive question, like, do you think that the systems are too reliant on gender cues? Like, think about how they performed before and after we reverse the genders. What do you think? Feel free to put in the chat. So our goal was to see if the systems relied too much on gender cues or if they could still work without them. The E2E system, which is the most commonly used, didn't show much of a drop in performance when the genders were reversed. And this actually suggests that it wasn't heavily dependent on gendered pronouns. While both the systems performed slightly better on the original data, the difference was really small. This shows that with enough context, the systems can ignore gender-based cues and still perform better. So let's move on to the conclusion. To sum it up, this study shows that the gender bias is a big problem in co-reference resolution systems. These systems often rely on societal stereotypes from their training data, which means they can perpetuate those biases. But the good news is that systems can overcome bias if they're given stronger alternative cues. The bias comes from from the data than the task itself. And the researchers have proposed effective devising methods that make the systems more resistant to gender bias without affecting their performance. And this actually lays important groundwork for projects like ours, where we aim to develop tools to detect and fix bias in large language models. So that's it. And in the next slide, we can see these are some of the additional readings that go deeper into the topics that we have discussed today. Yeah, that's it. Thank you.
Yeah, thank you. So everyone, now you have the opportunity to write your feedback form. Yeah, well, let me ask the question. Of course, if you have a question, put it in the chat box. So my question is, again, right, how the research you presented here is very important and valuable. Can you talk about how this can benefit the project of other groups? Of course, including your own group.
Of course. So, like, even for performing reasoning tasks, we see that bias often plays a very big part in those as well. We often see that even something as simple as, for example, writing maybe like a gender neutral explanation for anything, often our biases often perpetuate into those tasks as well. And if in the future we want to automate this task and have fair and equitable outcomes that would be great for everyone, then in that cases, gender bias, mitigating gender bias would be super important to do those tasks. So starting from like simply writing text to reasoning, this is something that needs to be addressed, and biases often seep into our minds unconsciously, but we can often train maybe models to do slightly better than us, hence, kind of having an equitable society.
Okay, yeah. Thank you. Any other questions? Okay, if not, yeah, prepare for quiz 2. It's not cumulative, therefore, what's covered in quiz 1 won't be covered by quiz 2. Quiz 2 is just from the end of quiz 1 until today's lecture. And I also uploaded the slides into Brightspace. Yeah, so we will have the quiz 2 next Tuesday. Good luck. Thank you. Bye-bye.